Hi, everybody, and thank you for joining us today in this Riskified technology meetup. So today we're going to talk about how Apache Spark can help us solve actual business problems in our day-to-day work. We will thoroughly examine one specific example and suggest a proper design to it. Along the way, we will encounter some cool technologies such as Databricks Delta Lake and others. We will also make use of some techniques which are usually associated with functional programming, such as type classes and semigroups. But don't worry if you're not familiar with these, as we will briefly explain them along the way. So our agenda for today. We will kick off by presenting an imagined scenario. I've sketched out a simple imagined problem for us so we can discuss it today. And it doesn't require much context, so we can dive right into the juicy bits. Then we're going to talk a bit about aggregations in general and how can they help us solve problems that more traditional architecture might fail to. We will also compare the solution to our imagined problem in both scenarios. We will then suggest a basic pipeline to handle batches of new data upon schedule to maintain our aggregation. Following up on that, we will dive deeper into what does maintaining incremental state properly really takes and how can we achieve it. To complete our journey, we will explain how the removal of information is reflected in the aggregation we maintain as we continuously refine them. We will conclude with some points you'd probably want to consider and discuss with your team when you're designing new aggregation-backed systems. If you have any question along the way, please type them here in the Zoom chat, and I'll try to address them midway into the talk and at the end of it. Okay, so let's start. And just before we do, just a bit about me. So I'm Eliav. I've been with Riskified for just a bit over 7 years now. I'm a classically trained musician, which means my BA is in music. It's in early plucked instruments, which basically is a branch of classical music, so to speak. And I love everything French, food, culture, music, whatever you name it. So that basically makes me a Francophile. That's the word for it. And just a bit about Riskified. So Riskified is a fraud prevention platform for e-commerce merchants. We are working with merchants from all kinds of industries, such as Macy's and Booking.com, and many, many, many others. We offer a complete product suite that allows merchants to do their business with a peace of mind throughout the full cycle of an e-commerce transaction. I joined Riskified when the company was about 15 employees, and today we're already over 600, which is really cool, I think, and we're continuously growing. Okay, so let's dive right into the problem we're going to be discussing today. So we are going to be working on some application called Blue Note, which is an imagined music streaming application, sort of like the applications you might have on your phone right now. Blue Note is the name of a famous jazz club in New York, but it doesn't really matter if you don't know it, so it's all good. And what we're asked to do is to present a new aggregation per user in the application's user info page. So basically the product team approaches us and asks for a new kind of functionality in the application. And there are many metrics that the product teams want to have in the user info page, but we will focus on just one to keep things simple today. We will focus on top-liked genres. So every song or track has a genre it's associated with. It might be classical, country, folk, whatever. And what we're aiming at is getting some kind of UI view that looks like that in the end. And of course, we're not going to be talking about UI today, but I thought it'd be nice if we know what we're aiming for. So here we see the user info page for Mary K223. And when she navigates to that page, she gets that kind of pie chart that you see here. So maybe she likes a lot of funk songs and a lot of rock songs and maybe some classical tracks because, I don't know, maybe she has some classical background like myself, whatever. And anything else going to the other category. And yeah, so basically we're trying to build something that eventually does this. And just like to settle things around, we were talking about an application which has the UI that the end users are actually using. So it has a player where you can look up for songs and pause and play and mark a certain song with a like. And there is the user info page, which is basically what we are want to be working on today. And obviously, that kind of an application is communicating with some kind of a backend server. It doesn't really matter what language it's written in, of course, and there probably is some kind of persistence layer. All in all, it's a very, very traditional and should be familiar kind of architecture. So, yep. Okay, so let's talk a bit about aggregations and how can they actually serve us well in such a problem such as we're facing here today. And as you can see from the title, I'm already giving in the fact that I think aggregations are great and I really love working with them. So let's see what we're talking about actually. So normally what we would do to present that pie chart that I've shown you a few slides ago, as in our application, we will go to the database, whatever it may be, and fetch all the information about a certain user. And then we get a lot of raw data. It might be like 10 tracks, might be 10,000 tracks. We don't know. We then crunch all this kind of information into some kind of meaningful data and present it to the user in our case. So the important thing to note here is that everything here happens when the user has sent the request, like the user has navigated to the user info page, and then all this kind of data munging, data crunching is happening in runtime. And basically what we're trying to get from a backend perspective is a document that kind of looks like this, if we're thinking about a JSON document. So we get user ID 13, and it has this kind of distribution of likes. So that user likes 2 funk tracks, pretty cool. But doing it the way we just described might be an anti-pattern when we're talking about big data. And I call this query everything. So let's see how it works and why do I call it this way. So assuming we're talking in a relational model, and it might not be, but it's just easier to talk about this. We might start our journey once the user is navigated to the user info page by looking up all the tracks that user has marked with a like. So we come up with 2 tracks, and then we go to track genres table and see that those 2 tracks are associated with the funk genre. Very, very familiar, very basic kind of approach. This gives us this kind of document after some basic crunching. But what else could we do? What is another approach that doesn't like do everything in runtime? So when we talk about aggregation-backed systems, what we're basically talking about is a system in which there is a separation between the data that the end user is consuming in the application and how it's created. So in that case, whenever a user marks a song or a track with a like, we ingest that kind of raw data and process it in some kind of another process that prepares the aggregation we want to be having before the user is actually making the request to get it. And then when they do make the request to get it, the meaningful data is already prepared. The question is already answered on that regard. So everything is kind of like ready for us to make use of. And we might want to have some kind of an aggregation reader on top of that, because we might not want to be, we're talking about another service, another process. We kind of like start to break things and get distributed. So we might not want to be talking to the same database from 2 services, but that's basically the same thing essentially. And the important thing is that in runtime, all we do is just like get the aggregation, that JSON document we just seen, we just like fetch it and present it. And it's a very different approach from the first approach we've examined. And all this kind of heavy lifting stuff happens when the user marks a like in our scenario, and not when the user asks for the aggregation. So aggregation comes with trade-offs. We're gaining faster response times, of course, because the document, which might be hard to compose in runtime, is pre-composed beforehand. And we get scalability in many scenarios because we no longer have the possibility of clogging our database with many queries in runtime. The queries the runtime is making are very simple. They just look for the aggregation by user ID. It's a very different concern for scalability, and the maintaining the aggregation is another concern that we can take care of. And we get cleaner separation of concerns. This is more like, it's more of an opinion of mine, but I think that when your backend server is not concerned with running complex queries, we've seen a rather simple example, of course, but it might easily grow to be much more complex. So your backend server no longer concerns itself with building complex queries and munging and crunching a lot of information and knowing a lot about this. It just fetches a record, an aggregation, which is another resource ready for it to use it. On the downside, we pay with data latency. This is inherent to any kind of aggregation-backed system in a way, because we no longer query our database in real time. We get some kind of a snapshot, which might be very recent, might have been updated 1 second ago, but can be also 1 day ago. It depends on how we're going to build our aggregation and how is it going to get updated. And something else that is sometimes overlooked is diminished agility. What I mean by that is that when we run aggregation-backed systems, and suddenly there's some kind of a change. Like in our scenario, we might want to be filtering a certain genre or remove a certain artist from the pie charts. So if we do everything in runtime, we just like add a simple filter clause on our results or whatever. And when we're talking about aggregations, we no longer have access to the raw data. So everything needs to be repopulated like from scratch. And when I mean everything, I really mean all the aggregations for all the users. So there are ways to facilitate this kind of work, which I think it's a great thing to do, but it's something else you need to take care of. So in an aggregation kind of mindset, this is something that if you overlook, it might bite you later on. And another thing that we pay with, obviously, is storage and compute. Which is something that sometimes people it might be off-putting for them because you're using a lot of storage and making a lot of computations to create aggregations for users, for all your users, and some of them might not even like navigate to that page ever. So this is like a trade-off you need to be thinking of. Do I need this response time to be super quick? Do I need this kind of information? Is it worth it for me to pre-calculate everything? If it's a yes, then aggregation might be the way to go. So at Riskified, we use Apache Spark to run aggregations. We use other tools, but today we're going to talk about Apache Spark, which solves some of the use cases, and I think it's a really great tool. If you're here, you're probably interested in Spark, so you know some of it, but I'm just like towing the line here so we're all aligned about what Spark is and what do we do with it. So according to Wikipedia, and I kind of like this definition, Apache Spark is an open source unified analytics engine for large-scale data processing. Spark provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. So the last bit is kind of like important and cool. Spark allows us to build systems which are described in a very high level, very business kind of domain modeling approach. And we don't need to take care of failures because in distributed systems, failures are going to happen. And we don't need to explicitly program our parallelism at all times because Spark knows that we want to be running these kind of processes in parallel, which is very cool. It allows us to stay focused on what we're trying to achieve. Basically, Spark runs a Spark process might be think of as a cluster that has a driver, which is kind of like the orchestrator for the whole process. And then there is a number of executors, which actually run the actual job to be done. And the job is like the jobs are splitted between executors, so each can take care of another part of the data. And normally, Sparks communicates with HDFS, which is might be S3 or Google Cloud Storage or whatever. It can work with other sources, and we will touch a bit on this point later, but that's like the classic Spark approach. And Spark itself is written in Scala, but Spark applications can be written in Scala or Java or Python or even R. Today, we're going to be focused mainly on the Scala, solely on the Scala flavor of Spark. And the reason is that the Scala and Java flavors allows us to use the dataset API and not only the data frame API. Now, if you don't know the Scala flavor, so basically the dataset API allows us to describe our data in a more type-safe manner, meaning that our instead of a data frame, which is just like a row, a lot of rows with any arbitrary kinds, types, dataset is actually correspondent to a Scala case class, which is a data structure that describes how each row looks like with specific types. This gives us the ability to build a system which is, in my view, more production adequate for production use, more production bound, more reliable, and more easy to understand and reason about. Spark can be used with various data formats because basically we're talking about reading and writing data, transforming information here. So we can use a lot of formats, but Parquet is kind of seen like the default, and we use it as a default as well. Parquet basically gives us is a columnar format, which means that every column is saved in a different file, and this allows for a huge improvement in performance as far as Spark is concerned. For example, if you don't need all the columns in a certain transformation, this is something that you cannot do in a CSV, for example, because it's a row-based format. Parquet also gives us compression by default, which is pretty cool. When we're talking about huge amounts of data, this might become crucial. And it allows us to describe nested data structures, which I find is a very super cool feature. Kind of because it's in contrary to CSV, for example, it allows me to think of the data I'm working with as if I was working with classes in my code that might be nested with a level or two. So this is something you just can't do with the CSV, and you can easily do with Parquets. If there are any questions in the chat, no, seem to be fine by now. So if you have any questions, feel free to type them in and I'll try to refer to them later on. All right, so we've covered the Spark 101. Let's go back to the problem we're talking about, Mary Kay and her pie chart. And try to suggest a simple way to solve it, which is not a query everything kind of approach. So in a basic kind of pipeline that Spark-based pipeline, we usually start by fetching the data. We need to bring in a new raw data. In our case, we might be wanting to update our aggregation on an hourly basis. So that means we'll have kind of a pipeline that runs on an hourly basis and does the same thing in every hour and keeps our aggregation updated. We start by bringing in new data, whatever new observations has occurred in our system in the last hour, for example, might be a day, your choice. Then we increment our aggregations using that data. We have some kind of state around about each user, and we use the new information from the fetch step to change it. And the last thing we do is we persist whatever newly arrived at aggregation we now have it at hand, and we persist it to our database of choice, which serves our application in order to make use of it in the application runtime. So let's talk about the fetch step a bit. fetching new information might happen in many ways, but let's think of a simple way, which is unloading information from our maybe data warehouse or another database for our hourly job. So we start by selecting the information we need: user ID, track ID, genre, and created at from the liked tracks table that we've seen. And the important thing here is that we scope our query to run on a specific hour. So we run between noon to 1 p.m. on a specific day. This describes basically the hour of the current aggregation we're now running. So this will change every hour. This is a dynamic part of the query. And we get something that kind of looks like this. We've seen something similar a few slides ago, but this is just information between in the hour we're talking about. And we get all the likes performed by users in our systems in that hour. And we unload it. In our case, we use S3 because we're on AWS, but you can use whatever cloud storage you're using. And we, as I've said, we unload it into Percat files. The next thing we do is we move on to the increment stage. So the increment stage basically starts off right where the fetch step just left us. So we start with reading that kind of data that we just fetched. And what we want to be doing is basically look up for all the information on that is all the likes done by a specific user, and just like reach the aggregation of the last hour given on that data, and then maybe bring in the existing aggregation that might be existing for that user from beforehand, like their all-time previous aggregation, and merge those two aggregations into some kind of a new updated aggregation, which represents the new all-time aggregation for that user. So in that case, we increment the count of the func genre count likes from 2 to 3, because they're from 1 to 3. Sorry, previously we've had 1, and now we've arrived at 2 new likes for func, so now we have 3. So that kind of mentality allows us to like continuously update our aggregations. And in the case of user ID 14, we arrived at that new aggregation for the last hour, and maybe they have no existing aggregation in our system. This will happen all the time, right? And what we do in that case is we simply persist the newly arrived at aggregation for that hour as their all-time aggregation. And lastly, we persist the information we arrived at in our database. This is actually all I have to say about this. We just need to take those two documents in that case and persist them to whatever storage we're going to be using eventually, maybe with a service that allows for easier reading on top of it. But let's talk a bit about the increment step, because there's kind of a lot going on there and we skimmed over it. So I think it's pretty interesting to inspect what's actually going on in there. So what does incremental state actually means? We start by reading a new batch, right? And then we're grouping by user ID. We've seen that in a very high level kind of way. Next thing, we calculate the aggregation per user ID. And then we join the newly arrived at aggregation for that hour with the existing aggregation that user ID has in our system. And lastly, we combine those two aggregations into the newly overall aggregation per user ID and persist that newly arrived at aggregation. So that's a lot. Let's break it step by step and see how can Spark do it very efficiently. Reading a new batch, that's pretty cool and pretty simple in Spark. So we can describe the case class sentiment. Case class in Scala just describes a certain piece of data. So in that sense, it's like sort of like a row in our database. So we have the user ID and the track ID and the genre and the created, just what we took from the unload and the fetch step there. But basically, Spark allows us to easily read this into a data set of sentiments, which basically describe a lot of sentiments. The next thing we do is we calculate the aggregation pair from what we just read. So I prepared two case classes for that purpose. One is ag and one is user ag. And the reason I've distinct between the two is because ag is of an aggregative nature. That means that this is the very aggregation itself, while user ag serves as kind of an envelope for the aggregation. So the ag case class has the genre liked, which is a map from string to long, because every key in our map is maybe we can think of as a specific genre, and it's pointing on a specific count of likes. And the user ag has the updated at, which we will continuously maintain, and the user ID we're talking about. And now let's see how can we actually like transform the data that we've read, the sentiments, data set of sentiments, into a data set of user ag. So we start by grouping by user ID and genre, and then counting each group, which brings us something that looks like a data frame that kind of looks like this. We have a user ID and a genre, and the count per user ID and genre. And the next thing we do on top of that data frame is we group that data frame by user ID, and then we run another aggregation on top of that grouped data frame, which basically what it's trying to do is to create a map from two arrays. So we kind of like zipping two arrays here. And every genre and every count is going to be paired together. So we kind of like get into a map and into a data frame that kind of looks like this. And this should starting to look kind of like we have on top in the case class, right? Kind of like starting to feel familiar in a way. Lastly, we kind of like tidy things up. So we created a nested column called ag, which basically just holds our struct, which is genre likes in that case. And we drop the top level genre likes because we no longer need it there. And we also update our appdated column to actually be the maximum time in our aggregation. So if we're talking about between noon to 1 p.m., so it will be 1 p.m. in that case. And once we've done that, we actually get something that is fully correspondative to the user ag case class, exactly what we need. And the as function just decodes that kind of data frame into a data set of user ag, which is exactly the return value of this whole expression that I'm showing you guys here. Right, that's looks like a lot, but actually pretty easy to grasp once you get like the Spark way of thinking about things. And lastly, let's see how can we like combine the previous knowledge we have about a certain user with the newly arrived at knowledge. So the native approach to do something like that is say, okay, I have some kind of a storage layer, maybe it's some kind of a database where I have the previously known aggregation for that user. So I'm just going to read it and combine the two ags, the new one and the historical one, into the new all-time aggregation and persist it back to the database. And this is very intuitive for most of us, I think. But there might be some caveats with that approach. So database reads might be costly. It might be, you might be paying per read, like in many databases has this kind of feature, and maybe you don't need to actually read everything to do that, and we'll see how in a bit. And also, if we're going to fail, if the process is going to be failing, we need to be paying for everything from the top, right? Because we said it's a distributed system, stuff might fail, and then what happens? We just need to run over again, and that's, maybe we don't have to do that. Maybe we can do something else. So what I'm suggesting we try to think of, and this is where stuff becomes a bit more interesting, is that we buffer our production database with something that looks similar to the production database, but resides in the HDFS layer of our system. So if our Spark application no longer needs to read from the production database, it can read and write to some kind of a replicate of our final representation in our production database. And then we can only update our production database with recently updated information, that might be pretty helpful to achieve what we're trying to do. So as you can see in this diagram, we're no longer reading from our production database. We're only updating it with writes. And to do that, we might consider using Delta Lake by Databricks, which is a very, very cool product I'm highly enthusiastic about. So what does Delta Lake gives us and how can it help us? Basically, the declaration for Delta Lake is that it gives ACID transaction over HDFS. That basically means that you kind of like feel as if you were working with a relational database, but it's actually Parquet files underneath. So they kind of like make it feel as if you're working with something that feels very intuitive and normal, and you can do normal database stuff over, but it's HDFS, which is what we want to be working with in Spark applications. And the reason that Delta is actually needed, I think, is there are many reasons, but one of the prime reasons is that updating Parquet is slow, because if you need to go over huge Parquet files, and Parquet files tend to be like big, and find a specific row and update it in place, that's going to be like might be slow and might like jam your continuous pipeline. So the way Delta handles this kind of problem is that they don't really update everything in place. They kind of like create layers of updates on top of the previous state and present to you the latest state whenever you need it. So it kind of like makes you feel as if it's updating, but it's actually just adding information or deleting information. And once in a while, you do want to like crunch everything and like make things smaller and not just incremental changes, changelog kind of way. But Delta allows us to do this whenever we want and not at all times, like we would do normally when we're updating Parquets in a simple fashion. So this is a pretty cool feature. And Delta is built to work with Spark. It's very, very intuitive to work in Spark with it, as we'll see in just a bit. And it works on HDFS. We're working with S3, so it's kind of like it's a perfect kind of match. And to connect us to where we were before, so what we could be doing and we will be doing now is that instead of reading and writing from our production database, we will read and write our aggregate. The whole aggregate is going to reside in what we call a Delta table, where our main Spark application that we've just described is going to be talking directly to it and no longer be talking to our production database. And there's going to be another Spark process, which is a very simple one that just takes the latest updated, whatever was updated in a certain hour, and upsert that into our database of choice. So in this way, we're remaining in HDFS land, right? I think it's a pretty cool thing to do because you stay true to the power of Spark in that way in many as one can claim. So how can we work with Delta tables in Spark? I think it's a very simple API, as you may see here. When you want to read an existing data frame data set, all you need to do is just like point it to where the actual HDFS resides, and it reads it as a data set of user agg. This represents, again, the historical knowledge of all aggregations we have about users. And when we want to join it with our newly arrived at new hourly aggregation, we just use the Spark API because this is simply a data set of user agg. So we're back in Spark land. And I'm using the Spark API for joins on data sets, which is basically join with, and I'm joining it by user ID. And what we're getting back is a data set of tuple user agg and user agg. And this is a key to understand where we're going next, because what we get from this expression is a data set where the left side represents the new hourly aggregation, and the right side represent the potential historical aggregation for that user ID. And I say potential, and you might see that it's a left join because the user might not have an existing user ID. So that's kind of like important to get this thing right. If you do inner join there, you're going to throw away all new entries to your aggregation. And then what we need to be doing is just like crunch that data set of tuple into a data set of user ag, because that's what we were aiming at. We want to be having a data set of user ag. So if we have we can just pattern match upon what we just arrived at. And if we get per row, no historical information, we just return the recent information. But if we do have an historical record for that user, so we want to be creating a new user ag where the app data that is coming from the recent aggregation because it's recently updated, and the user ID can come from whatever. But the aggregation, how is this going to work? So to answer that, basically what we're trying to do is combine the two aggregations together. So to answer that, what we want to be doing is combine the two, and functional programming kind of offers like a sort of a pattern to do that. It's a common thing that happens, and semigroup is the word we use to go for that. So by Wikipedia, there's this definition of semigroup, but we're not really going to use it because it's kind of like harder to read. It's pretty cool and useful. I'm going to suggest a simple definition for what a semigroup is and why is it helpful for our cause. So a semigroup is a neat, simple type class that allows us to describe how two instances of type A are combined into a single A. That means basically that we get a function of two A's, two user ag in our scenario, and how they're reduced into one. If you don't know what a type plus is, so basically it's just a piece of functionality that you can describe that a certain type has. So the type plus semigroup of user ag holds the knowledge of how two user ag are combined into a single user ag. So let's see how this looks in general. If we're talking about the semigroup for map, for example, what it does basically is that it looks for any key that is that matches, and then runs the semigroup on the value. So in that sense, you can see here that we're combining two maps with the pipe plus pipe operator, which basically says semigroup combine this for me. And what we get in return is a new map where the hello key points at 3, because semigroup found that the hello key exists in both maps and combined 1 and 2 into 3. And if you're wondering where the instances for a semigroup are coming from, they're imported from a library called cats, which basically implements this pattern and a lot more. I suggest that if you're interested in this, you might want to be looking into this. And when we know this, all we need to do in order to create a semigroup for ag, the case plus that we have, is just like semigroup combine the two maps of genre likes. Remember, genre like is a map from genre to the like count. So we just say that we declare a function of two args, x and y, and they're combined by combining the map. And that's pretty much it. And then coming back to where we were before we did this small detour to functional programming land, all we need to do is just like combine the historical and recent ag. And this is a very succinct, concise syntax, which I think is allows us to remain in a very high level approach. And then we're going to need to upsert this back to Delta. So Delta offers a very simple API to do that. All we need to do is actually like define how are we going to merge things. So we're basically saying if the user ID is equal, we call this a match. And when we have a match, we want to be updating everything. And when we don't have a match, we want to be performing an insert, which basically is the case where we don't have an existing aggregation for a user. This is a new entry. Very, very simple, very high level, very easy to reason about. But there is one thing we haven't talked about, and that's like the elephant in the room here. And this thing is, how do we actually handle the scenario in which a user has removed their like from a certain tracks? Because by now we've seen the whole thing. Very cool. We've seen how Delta works, how Delta helps us maintain this, and we have an aggregation running, assuming that we took care of scheduling it. But how are we going to make our aggregation correct if we don't take into account the fact that likes might be removed? So to answer that, we need to go back to the fetch step, actually, because we had some kind of a hidden assumption, which is pretty problematic that we took there. What we did was we represented each row in the fetch step as the existence of a like a certain user has marked upon a certain track. But whatever happens in that kind of modeling when a certain user removes their like from a certain track, is the row simply deleted? That kind of architecture for data can prove problematic. So what I'm suggesting you do, and it might need discussions with your data team to implement such a pattern, is that you move to a more event sourcing like architecture. So we no longer only add rows and delete them. We just add new events. If a user adds a like to a song, that's an event. If a user removes their like from a song, that's another event. You can see in the last 3 rows that user ID 14 has added and removed and then added again their likes for track ID 140 in just a span of a few seconds. Maybe they misclicked or whatever. So we know everything and we keep all the information we have. And this way we can at least know in the fetch step that a user has removed their likes. But what do we do in the aggregation with that kind of knowledge? And how can we adapt the cool Spark code that we've seen to make use of that information? So as you remember, we've seen the sentiment case class, which represented what we the data set of what we bring in from the fetch step. So we added the action field here, which represent whether the like was added or removed, and everything else stays the same. As far as our results, the ag and user ag, we leave that intact because nothing changes as far as what we want to be returning is concerned. And how are we going to solve this, actually? So a cool thing that we think about semigroups, we think about combining things, but combining things can be also thought of as subtracting things. See that example we have here, the hello key points at -2 in that on the right-hand map. And what we get in the end of that computation is that the hello key is pointing at -1 because basically it's 1 plus -2. That kind of way allows us to think about subtraction. So it's a cool way to adopt the semigroup to help us achieve what we want to be achieving. Because by now we just added stuff, but now we're starting to subtract, right? And when we use that, once we go back to the main chunk of that computes our aggregation, all we need to do is to take a look at the action column, and if it has like added, we count that column as 1. Otherwise, we count it as -1. And by doing that, everything else just sorts itself out. So, so our aggregation is going to be correct. And whenever users take their likes off a certain track, no problem. We're just going to take that into account. That's pretty much the whole thing. Of course, there's a lot to say about this and a lot to take into consideration. So just a few points that you might want to be considering. So don't forget to find what the proper data is. So if we just feed in new likes and we're going to miss on like removal, our aggregations are going to be incorrect very fast. That's a very big deal. And like backtracking this and fixing this might be hard. So really, we need to plan carefully when we're doing such, when we're building such aggregation-backed systems. And also, we haven't talked about this, but in order to bring our systems to a production state where we can actually make it work, we need to populate our database with an initial state. So it can use a lot of the code that we're actually we've seen here, but probably need some kind of a separate pipeline that allows us to arrive at the current state, and then we start running the hourly or daily stages. And testability, I think this is a very, very crucial thing for me. I regard Spark applications as production code that I want it to look great. I want it to look it's something that I'm happy to revise or review the work of a colleague. And I want it to have tests for everything I can have tests for. And everything we've seen here can have tests. The only thing that we cannot test is the merge to Delta part, because the API doesn't allow for testing it. So this is really important for me specifically in the choice to model what we did as we did and not as like one big script. And stack agnosticity, that's like the last thought I'm sharing here. We can use anything. Basically, we are very, very stack agnostic. We can use S3, but something else. And the database, we haven't talked about it. Like you can use anything you want. Doesn't really matter because we like buffered it to the end. And you need to bring your own scheduler, right? You need to be running this on an hourly basis. They're like the fetch step and the increment step and writing the results to the database. Something needs to orchestrate all this. We use Airflow, but you can use whatever you want. So I see some question in this chat, but just before we go into that, just a small recap about what we've seen to that, and then I'll take a few questions, of course. So we've seen batch processing as a fully fledged application. And we just talked about that, like how the way I want to be regarding Spark flows and we want to be regarding them in Riskified is that they are application, and we regard them with all the care and careful design we want to be having in production systems. Spark plus Delta is a great love affair. They work perfectly together, and Delta kind of like solves the problem of how to work with incremental state, but not actually work with the database, but at the same time not revert to just like raw parquets on HDFS, which is kind of like a middle situation solution, which is super cool, I think. We talked about identifying the aggregation and why is that important? Because we saw a simple aggregation where we just had one map. But some of our aggregations we run in production at Riskified might be much more complex, and allowing us to separate what is an metadata and put that in the envelope and concentrate on case classes that contain only the aggregations, and then we're able to define semigroup for them is crucial for readable and succinct code. So it's kind of like separating whatever the data is actually used for. And we've seen continuous refinement. We've seen how to take removal of flags into account, which is a pretty cool and important feature. And if you don't do that, you're just going to be wrong. And yeah, that kind of like might be the heavy lifting part where you need actually to change the way your data is modeled in your data warehouse or whatever you're bringing it from. But it's key and it's crucial. So don't forget to refer to that. So let's see if we have some questions before we finish here. All right. So we have one question. Is data new and historical is saved, bucketed to make join less painful and avoid shuffles as much as possible? So I'm assuming we're talking about the user. I'll answer for both sides. So when we bring in new data, yeah, we unload it as into its own bucket folder, whatever you not bucket partition folder, whatever you want to call it. So we read it's very easy to read only the information about a certain hour that we're currently running it. The aggregation itself, that's actually a debate. If we actually need kind of like a double partitioning strategy, which nullifies the idea of partitioning in that sense, because we need to find all the aggregations from all times per user ID, right? So we can't like partition by date on the aggregation side. What we found worked best is actually not, I found best not to partition on the aggregation end. And yeah, we monitor the performance and it doesn't deteriorate over time. And it still gives like super fast performance. So basically the aggregation is not partitioned, not by date and not by user ID. In addition to the question above, could the historical data be used for research as a log table? The answer is yes, very much so. This is another great thing about Delta. For example, we use DynamoDB, which is kind of like hard as an end, the production database. It's kind of hard for research teams to like make questions to that kind of database. And when we're putting stuff on HDFS, you can simply read it, which is, I think it's a huge, huge benefit of working in such a manner. So the answer is very much so, yes. All right, we have another question. Is it possible to configure different pipelines to feed one another? For instance, say we have a safety score aggregation for cars based on multiple parameters, and then we have another market value aggregations, again for cars, based on the safety score and other multiple parameters. Can we easily connect the results to safe? Again, this is like, I believe, if I understand the question correctly, I believe yes. All it requires is careful planning. You need to make sure that you're not like touching information which is out of scope for your process. I think what you're trying to do is read the result of some aggregation and another data to reach another aggregation. So basically, yes, you just need to schedule it. So on an hourly basis, you run the dependent aggregation after the first one. That's more of a question for the scheduler, which we didn't discuss here. We actually have a cool talk about Airflow in Riskified Technology YouTube channel you can check out. But it's basically a question of orchestrating it correctly. All right, I'm going to say that if I'm not going to make it to all the questions, I'm available on my email address, which is right here, and my Twitter, and I also blog on Medium. So feel free to reach out to me. Really, I'm happy to talk about this because I love this subject. But let's just see if we can squeeze in some more questions. So Eyal has this question. Can we configure the scale and or concurrent parameters, or does Spark figures those out on its own? For instance, if we want to aggregate by users, can we inform Spark to not compute the aggregation of events of the same user in separate parallel workers computation? Yes. Very important question, actually. Spark allows us it has a lot of good defaults, but we can control how many executors do we run and how the data is going to be distributed between executors. We can use the repartition by range function upon a data frame and data set, which actually allows us to tell Spark, okay, we're going to make a lot of transformations, which each needs the whole data a certain user has. It's a very useful thing to do in order to make things run faster. So yes, very much so. What are the ways to trigger the batch process? Great question. So as I've said before, we use Airflow as a scheduler. It's a scheduler that basically runs every hour and unloads data from our data warehouse, and then submits Spark jobs to our Kubernetes cluster, which uses the result of the unload, and it's all just like, it runs like an assembly line sort of mentality. If you don't need this on an hourly basis, you can manually trigger Spark jobs. If you're on Kubernetes, you can check out Spark on Kubernetes or whatever the way you're running Spark. We also have another talk in our YouTube channel about this, so look it up. All right. So that's pretty much all we have for today. Really, if you have any more questions, feel free to reach out to me over email or Twitter. Happy to chat about anything or consult, or maybe there is some cool suggestions that I'm missing. So thank you very much for joining us today, and follow the Riskified Technology blog on Medium, and feel free to reach out to us. And thank you, and have a great day. Bye-bye.